It is my pleasure to introduce Takayuki Osa. Takayuki Osa is an associate professor at the University of Tokyo and a visiting researcher at Riken. He will be giving a tutorial on dealing with the objective function with multiple extrema in robot learning. Takayuki graduated from the University of Tokyo and postdoced at and has been a professor at both Tokyo and Kyushu Institute of Technology. He has inspiring work in motion planning, reinforcement learning, and imitation learning. So this will be an exciting and informative talk. We're on a tight schedule today, so I'm gonna stop here and say, please take it away.
Okay, thank you. Thank you for the kind introduction. I'm so happy that I have so nice friends here. So yesterday we had a nice tutorial by Janet, and it was about state representations. And today I will mainly about action representation. And in this talk, I'd like to share my personal perspectives on objective function with multiple extrema. I think many of us are working to develop intelligent robots for the real world. And there are many applications of robot learning, and I have been also working at many applications like surgical robots, industrial robots, and construction machines. And when we apply robot learning to the real world, we often face several challenges. I think many of you have experience of feeling like, why does this robot move like this? And there may be a bug in your code, but there may be another reason, like there may be multiple solutions to your problem. For example, in motion planning, there can be multiple solutions. Even if you specify initial configuration and goal configuration, there may be multiple trajectories that satisfies your constraints. In motion planning, even if you specify the desired speed, then there may be multiple walking styles to achieve the desired speed. So if you apply an algorithm that finds a single solution to a problem with multiple solutions, then you may get unexpected solution in practice. In robot learning, we have to deal with various optimization problem. In motion planning, we have to find a trajectory that minimizes the cost function. In reinforcement learning, we have to find a policy that maximizes the expected return. In inner loop of reinforcement learning, we have to find the action that maximizes the Q value. And the existence of the multiple solutions are seen as multiple extrema in the objective function. If the objective function looks like this, there will be two solutions. And if the objective function looks like this, then there will be infinitely many solutions along the ridge of the cost function. And furthermore, in practice, sometimes we face this kind of highly complex objective function. And actually, existence of multiple extrema in objective function can be troublesome in practice. For example, in context of imitation learning, learning from diverse demonstrations can be challenging in practice. However, recently, I'm interested in discovering diverse solutions as a way to exploit multiple extrema in objective function. The reason I'm interested in it is that discovering diverse solutions can be a way to build a skill library. Let's think about the difference between human adults and kids. Actually, human adults can learn a new task very quickly, but kids cannot learn a new task so fast as adults do. I think that the critical difference is experience. Human adults have experience of doing various tasks, and they have skill libraries internally. And it enables us to perform few-shot adaptation to new tasks. Actually, the robot learning community has developed various frameworks to exploit the skill libraries. However, in practice, it is not so obvious how to construct such skill libraries. I think that if we can extract diverse behaviors from a single task, that would be an efficient way to construct such skill libraries. So that's a motivation. So recently, I'm working on this kind of discovering diverse solutions in robot learning. So in this talk, I'd like to share our experience on motion planning and reinforcement learning. So first, I will talk about motion planning part and then move to reinforcement learning. And in the end of the talk, I will share our experience where we faced multiple extrema in the Q function. Okay, then let's begin with discovering diverse solutions in motion planning. So first, I'd like to briefly review the categories of motion planning methods. In my personal opinion, there are 3 categories of motion planning methods. First, we have an optimization-based method where a trajectory is planned by minimizing the cost function. And another popular method is a sampling-based method where a trajectory is planned by sampling various configurations and connecting collision-free nodes. And these methods are actually very robust and work very well in complex environments. The third category I'd like to include imitation-based method. If the demonstrations are provided by the expert, we can model the demonstrated trajectories and we can adapt it to a new scene. So yesterday we had a great talk by Ald, so I don't have to mention very much about it. Then from the next slide, I will focus on the optimization-based method. However, I will believe that the lessons obtained from the optimization-based method will give some insights to other categories as well. Okay. Then the problem of trajectory optimization for motion planning can be formulated as like this. Here, psi is a trajectory and c is the cost function. The question I ask today is, how many solutions are there? So let's think about this case. Let's suppose that initial configuration is given by this figure, and this is a goal configuration. And how would you move the hand from the initial position to the goal position? And actually, there are many solutions. You can move the hand over the obstacles, or you can move the hand behind the obstacles. And let's look at the simpler case. So here we think about a trajectory from the blue point to the red point and avoid these obstacles. Obviously, there are at least 2 solutions like Xi1 and Xi2. And actually, there is a continuous deformation from one to the other. In this case, these trajectories are called homotopic. And homotopy is a term in the field of topology. Actually, prior work on motion planning has been aware of the existence of homotopic solutions. And some of the studies propose topology-based representations, and they use them for motion planning. And some other studies propose methods for discovering multiple solutions in motion planning. And from the next slide, I will talk about our methods to find multiple solutions in motion planning, but it's just an instance. So if you're interested in this direction, please check these papers as well. Okay, so in our approach, we will format the problem as density estimation, and let me illustrate this. So suppose that we have a cost function look like this. Then our goal is to find these 2 points. So what we do is to generate samples from a proposal distribution, and we compute the cost corresponding to each samples. Then we give a higher weight to a sample with a lower cost following this form. Then we obtain this density. The modes of this density actually corresponds to the solutions that minimize the original cost function. In this way, the cost function appears as a density. And if we use this kind of important sampling technique, we can reduce the problem of minimizing cost function into that of estimating the density. Okay, so I will format this problem more properly here. So first we consider the maximization of R instead of minimizing C. Then we consider target distribution given by this form. Here, F is a kind of shaping function, and F is always positive and monotonically increasing. And here, P prop is a proposal distribution which we use to generate samples. Here, and this kind of shaping function has been used intensively in the field of reinforcement learning. And yeah, then we approximate this target distribution using a parameterized model. And this problem can be formatted as minimizing the Carey divergence between target distribution and our parameterized model. Then the solution to this problem can be given by maximizing a weighted loop likelihood. And if we use the multiple distribution as P theta, then we can estimate the multiple modes simultaneously. So that's what we do. And here we format the problem as an inference problem. And we can quickly show the connection to minimizing the cost function. And first we consider the surrogate objective like this, and now we consider expectation because we are interested in multiple solutions. Then the solution to our inference problem is given by weighted log likelihood like this. In the context of reinforcement learning, previous studies showed that this weighted log likelihood is actually the lower bound of this surrogate objective. So this is a connection between our inference problem and minimizing the cost function. Okay, and there is a clear connection to KL-regularized reinforcement learning actually. And in the field of reinforcement learning, Jan Peters showed that the solution to this reinforcement learning problem with KL divergence constraint is given by this form. Yeah, this target distribution. So actually, this is the same as what we are using in our motion planning framework. So in other words, so in our motion planning framework, we are implicitly using this KL divergence constraint. However, the meaning is a bit different. In reinforcement learning, we don't want to make policy jump between different modes. This is the reason why we introduced this KL divergence constraint. We want to keep the policy update within the trust region, and we want to obtain the monotonic improvement of the policy. So somehow we expect this behavioral policy to cover local region and not to cover diverse behaviors. However, in contrast, in our framework, we use wide distribution for this proposal distribution, and we expect to cover diverse behaviors. And by using this implicit constraint, the solution should also cover diverse solutions, and we approximate it using the multimodal distribution. So this is the reasoning of using this kind of constraint. Okay, then as our methods are based on importance sampling, it is essential to use proposal distribution that covers diverse behaviors. And for this purpose, we use the sampling strategies used in STOMP. And this is a very classical method, but it's very easy to use and it works very well. If we use this technique, we can generate a random but continuous trajectories and that start from 0 and ends in 0. And this is very useful method. And I recommend it to you if you are interested in generating this kind of random trajectories. Okay, and now we format the problem as inference, but the result of inference may not lead to the exact solution of minimizing the original cost function. Therefore, we need fine-tuning of the trajectories. And for fine-tuning, we use CHOMP, and CHOMP represents covariant Hamiltonian optimization for motion planning. So here is the update rule of CHOMP, and this term is actually a trust region term. And in the standard implementation of CHOMP, we can maintain the velocity profile before and after the trajectory update. And this property is very suitable to our framework because we can keep the shape of the trajectories as much as possible, and we can avoid jumping between different modes. And if you're new to the field of optimization-based motion planning, I recommend you to check this paper. Okay, then here is a summary of our algorithm. So I call this algorithm SMTO. So first we generate samples from proposal distribution, and we evaluate the costs, and then we do the density estimation using the importance weight. And if necessary, we fine-tune the trajectory using CHOMP. So here is a result of discovering multiple solutions here, and we could find 3 solutions here. And this is another example, and we can find a different way to approach the object. And the video I showed in the beginning is actually one of the results of our method. Okay. So far, I showed how we can find multiple solutions. The next question is the number of solutions really finite or not? So if you look at these 2 solutions, now you will think that there might be another solution in between. And if you look at these 2, then also you will think that there should be something another here. And if you repeat this, probably you will now think that there should be infinitely many solutions for this motion planning problem. So in the first method, we implicitly assume that a number of solutions is finite. However, in practice, a number of solutions may be infinite. And if the cost function looks like this, there will be infinitely many solutions along the ridge of the cost functions. The question is how to model infinitely many solutions and capture the solution manifold in a continuous manner. In the first method, we use a model with a discrete latent variable to model the finite number of solutions. Then now we use a model with a continuous latent variable and try to capture the solution manifold. Then to train this, we use variational autoencoder. This is very straightforward. So the objective of variational autoencoder is derived as a lower bound of the marginal log likelihood. And I said that we can obtain multiple solutions by maximizing weighted log likelihood. Then if we connect this weighted log likelihood with the lower bound of the likelihood, then we can train the variational autoencoder in a way that the latent variable captures the solution manifold. So let me show you the example. So suppose that we have a cost function here, an objective function here. Then we generate samples from the proposal distribution. The proposal distribution is uniform in this case. Then we evaluate the importance of each samples. Then we can train the model in a way that it outputs the samples along the ridge of the objective functions. So here is the procedure of the second method. So the procedure is almost the same as the first one, but we use a different model and we slightly modify the objective function. And here is the example of maximizing the toy objective function. So top row shows the result of our method, and the bottom row shows the result of a cross-entropy method with multimodal sampling distribution. If you use multimodal sampling distribution for cross-entropy method, we can obtain multiple solutions. However, we cannot cover the solution manifold continuously. By contrast, in our method, we can capture the solution manifold continuously like this. However, there is actually a failure case. And in this objective function, we have a unique solution, but our model learned the manifold along this direction due to the gradual slope of the objective function. Again, what we are doing is just an inference, so we cannot learn the exact solution. So we need a fine tuning. So here we have, there is an example of the discovering diverse solutions for motion planning. So we can continuously change the type of the solutions by changing the value of the latent variable. And here's another example. And in this video, and the effector goes from the right-hand side. And in this video, the end effector goes from the left-hand side, and we can continuously interpret the solutions. The good thing of this approach is that we don't need any demonstrations. We can just sample the many trajectories, and we are just solving the optimization problem. Okay. And here is a visualization of the discovered solutions. So in this case, we use a two-dimensional continuous latent variable for the second method. And we can cover the solution space continuously as shown in these colored circles. And the solutions found by the first methods are represented by the triangles as shown here. And actually, the first method can also find well separated and represented solutions in motion planning. The benefit of discovering diverse solutions is that we can quickly adapt to the change of the environment. For example, if we add a new obstacle in the scene, then some of the solutions cannot be used anymore. But if we have a set of feasible trajectories, we can quickly find a usable one. I think this setting is very realistic if we have a fixed manipulator in the environment where we have a static object and movable objects. Okay, so I will wrap up the first part. So first of all, there can be many solutions in motion planning, and if you can find multiple solutions, then we can quickly adapt to this change of the environment. And I'm interested in this field because there are connections to various fields, including topology, optimization, reinforced learning, information geometry, and generative models. And also there are many open problems here. So to me personally, I have just worked on static objects, but it would be great if you could develop diverse reactive policies for moving objects. And also it would be great if you can extend this framework to task and motion planning. Yeah, of course, maybe some of you may be working on it already, but yeah. Okay, then let's move on to the discovering diverse solutions in reinforcement learning. Okay, in reinforcement learning, actually, also there can be multiple optimal policies. So it's a well-known fact, and it's also written in a famous textbook of reinforcement learning. Although the popular reinforcement learning algorithms such as software critic and TD3 finds a single solutions, there are many studies that address this direction. And the benefit of discovering diverse solutions is, again, that we can do few-shot adaptation to a new environment, and also we can compose complex behaviors just by mixing and sequencing primitive behaviors. From the next slide, I'd like to explain some basics of discovering diverse solutions in reinforcement learning. Okay, so to model the diverse solutions, typically latent condition policy is used. In general, the policy is defined as a conditional distribution of action given state, and we use this form specifically in this case. And if you recall the model I used to model diverse solutions in motion planning, they are actually analogous. And this part is called latent condition policy, and this policy shows the different behaviors with different values of the latent variable. And this part is a prior distribution, and typically we use uniform distribution. And if we use uniform distribution, it means that we train different behaviors equally. And when we generate latent variables, we sample the latent variable from the prior distribution in the beginning of the episode and fix it during the training. And to obtain diverse solutions, existing method often use the objective function in this form. So the objective function is usually given by the sum of the task-related reward term and the diversity term. And when we design an algorithm for discovering diverse solutions, there are a few important design choices. One is an algorithm for updating policies. One popular choice is reinforcement learning-based algorithms such as TD3, software critic, and PPO. Another popular choice is evolutionary algorithms such as CMAES. Actually, in the field of evolutionary computation, the methods for discovering diverse solutions are actually popular, and such methods are often called quality diversity algorithm. And another important design choice is diversity term. In the community of reinforcement learning, I think mutual information-based metrics are popular. And in the field of evolutionary computation, I think the distance-based and map rates-based metrics are also popular. And from the next slide, I will talk a little bit more about maximizing the mutual information using the reinforcement learning-based algorithm. Maximizing the mutual information is often performed in machine learning in general. However, directly computing the value of the mutual information is often challenging because it involves the density estimation of marginal likelihood. So to make the problem tractable, variational lower bound of the mutual information is often used instead of mutual information itself. So when we introduce the auxiliary distribution to approximate the posterior distribution, we can quickly obtain the lower bound as shown in these equations. So in this case, I showed the case where we use mutual information between state action pairs and the latent variable. So if you're just interested in maximizing mutual information between state and latent variable, you can simply remove A from these equations. And here, this equation implies that what we have to maximize is just expected log likelihood. And this is tractable in practice. So what we have to do is reconstruct the latent variable from the state action pairs. That's it. So recently, we investigated different strategies for maximizing the mutual information. So first, the design choice is whether we should maximize state action-based mutual information or state-only mutual information. And second design choice is whether we should maximize the mutual information through the posterior or through the critic. Okay. First, I will explain the difference between the state action-based mutual information and state-only mutual information. And suppose that we have a Markov addition process given by this figure. Here we have 5 states and 3 actions are allowed in each state. The agent receives the reward when it reaches S1 or S4. And there are many solutions, many optimal processes for this MDP. And 2 of them are shown here, Pastor 1, Pastor 2. Here, these policies are obviously different, but the interesting thing is that the visitation frequency, state visitation frequency is the same between these two policies. And what happens is that the posterior distribution Q of Z given S cannot quantify the difference between pi star 1 and pi star 2 because the state visitation frequency is the same. So in this case, maximizing state-only mutual information cannot encourage the diversity like pi star 1, pi star 2. However, if we take action into account, then we can quantify the difference. So in this case, it's better to maximize the state action-based mutual information. And the previous studies often maximize the state-only mutual information, but it's suitable for their tasks. So for example, when we train agent to work in diverse directions, it's suitable to maximize the state-only mutual information. However, my message is that it's good to be aware that there can be a Markov decision process where it's better to maximize state action-based mutual information. And this design choice brings another design choice. So when we maximize the state-only mutual information, we consider the posterior given by this, and we maximize this log likelihood. However, this posterior does not take action at it is input. So even if you want to maximize this objective, we cannot directly back propagate the gradient from the posterior to the actor. So what we do usually is to deal with the output of the posterior as the unsupervised reward and approximate it using the critic. Then we back propagate the gradient from the critic to the actor. However, if we maximize the state action-based mutual information, the lower bound is given by this, then the posterior actually takes the action as it is input. So in this case, we can directly back propagate the gradient from the posterior to the actor. So the difference is that the gradient from the critic is actually biased unless we use a compatible function approximation. However, in the second approach, what we are doing is maximum likelihood estimation, which is unbiased. So in practice, the second method could be more stable. So we investigated this difference empirically. So in this task, here we use a task on Mujoko, and we modify the velocity term in the reward function to intensify the existence of the diverse solutions. So here in this task, we observed that maximizing state action-based mutual information through the posterior led to the most diverse solutions with most stable learning process. Okay. Then here is a visualization of the obtained locomotion behavior. So in this case, we learned the two-dimensional latent variable. And if we change the latent variable in this direction, we can change the angle of the knee continuously like this. So here the knee is stretched and here knee is bent. And if you change the latent variable in this direction, we can continuously change the locomotion behavior from two-leg walking to the one-leg hopping. So in the bottom, the agent is working with two-leg walking, and then here it's hopping with one leg. Okay. Then if you look at these two frames and this red frame, this red frame is a kind of the mixture of these two blue frames. And this kind of continuous mixture of the behavior is a kind of benefit of learning continuous latent variable, in my opinion. And we can obtain similar result on hopper. So if we change the latent variable in this direction, we can change the angle of the lower joint continuously. And if we change latent variable in this direction, we can change the angle of the upper joint continuously. And again, the locomotion in this frame is a kind of mixture of these two frames. Okay. Then once we obtain the diverse behaviors, we can quickly adapt to a new environment just by searching for usable behaviors. So this is the obvious benefit of learning diverse behaviors. And another benefit of learning a latent continuous latent variable is we can continuously switch the working behaviors. For example, in this case, we can switch how to hop during the episode. And in this example, we can continuously switch from two-leg walking to one-leg hopping. And this kind of switching could be enabled if you learn the continuous latent variable. Okay. So before concluding this part, I'd like to give some remarks. So feature adaptation by learning diverse solutions in reinforcement learning is shown by this paper. And also the composing complex behaviors by changing the latent variable is also shown in this paper. So there are actually many previous studies. So if you're interested, please check these papers. In this talk, I didn't have much time to talk about quality diversity algorithm, but actually there are many nice work there. So, and actually there are nice survey papers. So if you're interested, please check these survey papers. And of course, there are open questions in this field. So as I said, there are many forms of diversity term to obtain diverse solutions. And still the committee is developing this kind of diversity metric. So still it's ongoing. And also, it would be great if you can learn a meaningful skill space, but the learning the meaningful latent space itself is open questions in generative models. For example, we are still watching the progress of the diffusion models in the field of generative models. Then like that, the learning how to meaningful skill space in reinforced learning is also open questions. Okay, then in the last 5 minutes, I'd like to share our experience where we faced multiple extrema in the Q functions. So far I talked about discovering diverse solutions as a way to exploit multiple extrema in objective function. However, I would like to mention that we have to be aware of multiple extrema even if you are not interested in discovering diverse solutions. Okay, so recently I'm working with manufacturer of construction machines, and our project, we are doing the project where we aim to develop reinforcement learning algorithm to automate construction machines. In this study, we aim to develop a method for learning to plan a trajectory using depth images like this, and we try to excavate the target area efficiently. And in the end of the episode, we want to obtain this kind of flat surface. This task looks very easy, but it's not. And this is the interesting point of this task. To reduce the number of actions, we want to make the bucket always full. But in the end of the episode, we want to obtain the flat surface. So we avoid excavating a small amount of soil just for making a flat surface. That's the challenging part of this task. And in this study, we compared Qt-opt, TD3, and software critic. And before explaining our result, I will quickly review the difference between Qt-opt and TD3. There are differences mainly in the policy representation. In Qt-opt, we search for the action with the highest Q values using cross-entropy method, which is a stochastic optimization-based method. So we do not have explicit policy model in Qt-opt. In TD3, we have a neural network that outputs action in a deterministic manner, and we train the actor network by maximizing the expected Q value. The training of the critic is almost the same in both methods, and we employ double-crypt Q learning, and the difference is just how to generate actions when we compute the target Q values. So the difference is just how to generate actions. And in this study, we observed that Qt-opt can learn appropriate policy to excavate the target area. And here is the learning curve. And in this study, we propose a variant of Qt-opt to improve the sample efficiency. However, this is not the point of this talk. So I would like to focus on the fact that Qt-opt significantly outperformed TD3 on this task. So as I said, the difference is just how to generate actions. The question is why the difference in policy representation led to this significant difference in the performance on this task. So when we analyze this result, we notice the interesting property of this task. That is, there are multiple actions that achieve near optimal Q values. Let's think about this state. Here, this is a state after the first action, and this part was excavated in the first step. And if we excavate here in the second action, follow the policy trained by the Qt-opt, we can obtain the near optimal result. And if we excavate this part in the second step, then again, if we follow the optimal policy trained by the QT-opt, then we can obtain, again, the optimal result. So this indicates that there can be multiple actions that achieves near optimal Q values. So to analyze this result, we visualize the Q functions. On this task, the actions are three-dimensional. So we visualize the maximum Q values over the third dimension. So here is a pair of the state and the visualized Q function. And here, the dense red region shows the distribution of optimal actions. So obviously, the distribution of optimal actions are very complex and multimodal. And the unimodal policy, for example, Gaussian policy can be drawn as a circle in this figure. So obviously, the shape of the dense red area is more complex than Gaussian policy, a circle in this case. Then, so this result indicates that unimodal policy may not be expressive enough for this kind of excavation task. And we have another empirical result that indicates the effect of the multimodality of the optimal actions. In QT-opt, we use a cross-entropy method. And here is the procedure of the cross-entropy method. First, we generate samples from the proposal distribution, and we compute the score, and we keep the top samples. And then we update the sampling distribution by fitting it to the elite samples. Then we iterate this process in cross-entropy method. Usually, the output of the cross-entropy method is given by the mean of the elite samples in the last iteration. And we changed the output with best sample in the last iteration. And actually, it led to the improvement of the performance of QT-opt in this task. Actually, taking the mean of the elite samples is equivalent to fitting a Gaussian distribution to the elite samples. However, if the elite samples exist in the separate modes, taking the mean is actually the bad approximation of the optimal actions. So this case study indicates that we should be aware of multiple extrema in the objective functions, even if we are not interested in discovering double solutions. Okay, so this is almost the end of the talk. So in this talk, I mainly talked about discovering double solutions. And I think that this will bring us flexibility in robot learning systems. I see the discovering double solution as a way to exploit multiple extrema in the objective function. At the same time, even if you are not interested in discovering double solutions, we should be aware of multiple extrema in the objective function because it will affect the performance significantly sometimes. Yeah. Okay, this is the end of the talk. So I hope you enjoyed my talk. Thank you.
We have some time for questions.
Thank you very much for this nice tutorial. We also noticed that you have often these multiple optimas when you do planning, for instance, like the first part of the talk. But then often we would like to distill policies from this, right? Like learn a policy to do it faster, that you don't have to run the planner on the online. And there we had even more problems with this multimodality. So what would be your, maybe what's your choice there? Do you want to get rid of the multimodality that you have better training signals, or use a policy network that can deal with multimodality by itself?
As the question is that by considering the multimodality, we can get better optimization procedure or not? What is it?
Yeah, I can either change my optimization procedure or my reward function that it collapses onto one solution. Yeah. For instance, by conditioning it on the policy, like guided policy search type of things. Or I can make take a policy network that can deal with multiple solutions and can learn all of them. Anyway, maybe this was too detailed. Sorry about that.
Yeah, but so there are many ways to deal with multiple extrema in the objective function. In my opinion, if you explicitly deal with a multiple extrema, probably we can sometimes avoid falling into the bad local optima, and then we can select the better one during the optimization process. And that's will be one point. And yeah, And here, I couldn't show very well that benefit of discovering diverse solutions very well. But if we think about the downstream tasks, it would be great if we can have multiple solutions. That I think probably the benefit will be there, not like improving the optimization process itself. But yeah, that's my
keep the multimodality around. So yeah, your advice is to keep the multimodality around as long as you can, sort of.
Yeah.
Good point.
Thank you.
Great talk. For the diversity terms, so you mentioned a couple of different ones. Are there sort of general rules for when you recommend each one, or, and do you think ultimately there's going to be kind of one specific diversity term that is generally applicable, or?
So the question is about how to select a good one for your task. So the point is that what is the most parsimonious representation to obtain the information of your task? And then, for example, when we train the agent to work in the diverse directions, probably the location of the agent, like XY coordinates, will contain the most of the information. And if you include more, then that will be too redundant. Then, yeah, so probably you have to select the diversity metric based on what kind of diversity you want. Then that's my answer. I'm not sure. Yeah, but yes.
So in your first part of your talk, you talk about the sampling-based method, which you said something better than the CEM, right? CEM converge can only have a very sparse coverage of the whole space. But in your second part, when you use Qt-opt, have you thought about using some better sampling method than just the CEM? Like something you mentioned in the first part of the task motion planning.
So using a better sampling method for the first part of the motion planning? Right?
Yeah, because you mentioned something like you say, oh, by using that energy-based way, you kind of have a better sampling than CEM, right? Which is approximate for Gaussian.
Okay. So actually, I didn't use cross-entropy method for sampling.
That's for the Qt-opt. You are using cross-entropy.
You mean the Qt-opt?
Yes.
Okay. So actually, there are many methods that improves the Qt-opt, and then so there is a method that uses a better or sophisticated policy for generating samples and when we find the action in a stochastic manner. Well, so yeah, so we could use that, but yeah.
Thank you.
Any more questions? So I actually really like this talk. Thanks for giving it.
Thank you.
One of the things I really liked was that part where you showed the multiple ways to get a solution in the optimization. And it made me think, the path over the plant example. It made me think, well, then how do you choose among all those options once you have that, same cost ridge? I was wondering if you could maybe opine on that a little bit.
Yeah, that's a good question. So actually, I don't have a clear answer to it, but so we can do that we can select the best answer based on your preference. So for example, if we apply this kind of robotic system to the daily life, and if the user is not an expert of the robotics, then probably the user may have a particular solution in their mind, but the cost function may not specify the unique solution that the user wants. Then in that case, we can simply obtain the diverse solutions using a generic objective function and then propose candidates of the solutions. Then the non-expert user can choose the preferable one based on his preference. So that's maybe one of the ways to select the solution.
More questions? All right, I'm going to take the opportunity to ask one more. So it seems to imply to me that you almost are saying that you could do like a recursive application of this. Is that like your first optimization gets the ridge, the second optimization gets
points along the ridge, and then a third optimization could find even more cost extrema. Like you could just keep on sort of finding a new Pareto optimal cost ridge. Is that true with your method?
So you mean that, are you asking about the cross-interpret method or the what?
So you compute that cost ridge, right? And then when you're doing like the user preference example, you're going to get their cost along that ridge.
So the cost in that place. I don't get that part.
Maybe I'm phrasing it wrong. So suppose you have a user with multiple preferences that are equivalent.
Yeah.
So now you've got this new landscape of problems that are all the same solution, all the same cost, right?
Yeah.
So could you apply your method recursively?
I see. I can understand it. Yeah, probably we can do that. So once we learn skill space based on the genetic cost, and then we can train a new policy to fine-tune the solution even more based on the user's preference, and then we can learn the better policy in the field in a low-dimensional latent space. So probably that the second learning stage will be much more efficient than learning in the parameter space of the trajectory. Yeah.
All right. Oh, we got a question way back there.
Sorry, I've lost my voice, so I'll try to be clear. Hi, Takayuki. This is Old. In the first part of your talk, you presented methods to project into a latent space. And from the slide 25, it looked like the latent space was higher dimensional than the original space. So could you comment on the dimensionality of the latent space? And I also wanted to have a clarification on whether you have an explicit expression for the region that is of high cost, or if you still have to sample to find yourself in the region of the high cost. I'm sorry, I've lost my voice.
Thank you for asking a question. So the question is about high dimensionality of the trajectory representation. Did I get it?
Yeah, the dimension of the latent space.
Okay. So regarding the dimensionality of the trajectory, so in the first part of the talk, I used waypoint trajectory representations where the time step is 50, and we tried 7-dimensional, but we tried a manipulator with 7 degrees of freedom. So in that case, we have the 350 dimensions for each trajectories. And if we simply use it for partial autoencoders, then we need to sample I think 20,000 trajectories to train the model, and then it took me 30 minutes to train the model. However, we can also use something different trajectory representation, such as dynamic movement primitives. In that case, we can introduce the inductive bias to trajectory representation, and we can actually reduce the necessary number of the trajectory samples, like the 5,000. And in total, the training cost became 5 minutes in the end. So if we use a proper trajectory representation, then we can reduce the training cost in the first part. So what was the second question? Sorry about that. Okay, thank you for the. Actually, we tried what latent space, like 2-dimensional solution space and 1-dimensional space and a 3-dimensional space, and we tried that. But so actually, when we increase the number of the dimensionality of the latent space, we didn't get diverse solutions anymore. So probably 2 is already too much, and then 1 was usually sufficient. And the diversity of the solution are defined by the landscape of objective function itself. So increasing the number of the latent variable may not lead to the more diverse solutions in practice. What was another question?
Hey, there's another question from online. The question is, state-only conditioned posterior function cannot discover trajectories in an inverse direction. So he wonders why can't model in the posterior by memory network, such as RNN something, so the direction can be captured.
So you mean that, well, so if you use a sequence of the state, probably we can reconstruct, we can quantify the difference. If that's what you're asking. But yeah, so okay, so when we max, so in that case, in this case study, we just use the state as a single time step. But so of course, if you take into account the sequence of the state, then we can also extract more information. So we can encourage more diversity using that metric. Yeah, so yeah, that's my comment.
Yeah, thank you.
So we're out of time. Let's thank our speaker once again.